Welcome. In previous videos on SQL, we introduced the select statement, and we demonstrated how this statement could be used to retrieve data from a database table. In the current lecture, we'll be introducing a very powerful capability of SQL that allows us to summarize data. With the operations we'll introduce, we'll be able to derive values based upon what is stored in the tables. And this capability provides a set of valuable tools for data analysis. Once again, all of our examples will be focused on using just a single table. Let's consider just what we want to accomplish in this lecture. One of our goals will be to distinguish between scalar and aggregate functions. An aggregate operation operates on a group of rows and generates a single value for that group. These operations may be used in operational data stores or transactional databases, as well as data warehouse environments. We also hope to introduce the common standard aggregate functions. We'll not show all of them because there are quite a few supported by today's commercial relational database systems. We'll explain the concept of grouping rows in order to apply a function. We'll also explain the effect of the argument's data type when determining the result data type of a call to an aggregate function. Furthermore, we'll discuss the removal of unwanted rows in the final result set. And we'll also explain the logical order in which operations are performed when we have a complex SQL statement that involves grouping and aggregate functions and removal of some of these groups. Aggregate functions operate on groups of rows and generate a single row for each group. For this reason, an aggregate function is sometimes called a group function. An aggregate function returns a result that has the same data type as the data type of the argument which was passed to the function. In our presentation, we'll discuss the following ANSI SQL 1999 aggregate functions: average, max, min, sum, and count. There are additional functions that are supported by commercial products, but these are probably the most commonly used functions that you should be aware of. Now, an aggregate function is used to scan a column of selected values and perform a computation based on those values. The result of an aggregate function is always going to be a single value regardless of the number of rows upon which the function actually operates. In contrast, a scalar function, which might also be called an individual function, operates on a one-to-one basis. A single value from one row is passed to the scalar function, and a single value is returned. Such functions may often be used to do things like data type conversion or casting from one data type to another. Let's consider this example here that asks, what is the total lab fee for all computer science courses? So the from clause identifies the course table. The where clause includes a predicate that identifies just the rows for courses sponsored by the CIS department. The select clause invokes the sum aggregate function, and what is passed to that function is the C lab fee value from each of the rows that satisfies the predicate. So the sum function returns the sum or the total of the values in the specified column. Therefore, the sum can only be applied to numeric data types and intervals. The column heading for displaying the result of an aggregate function is determined by whatever implementation you're using, either the particular DBMS or more specifically, the front-end tool that you're using. Therefore, it's good practice to supply a column name for this column because it contains a derived value. This is why we rename the column in this query. Now note that the data type of the value returned by the function will be determined by the data type of the argument. That is, whatever the data type of C lab fee is within the course table, this will also be the data type of the result of invoking sum and passing it C lab fee as an argument. This is of particular interest for systems like SQL Server and DB2, which are perhaps a little bit more respectful of the ANSI SQL distinction between an exact numeric and an approximate numeric. Let's take a close look at exactly what is going on in this query. The first thing we note is that the where clause will identify 6 rows from the course table. All of these rows will have a C department value of CIS. From those 6 rows, the lab fee values will then be passed to the sum function. If we simply say select sum lab fee, then the column heading that's produced depends upon the tool that we're using. Because we're using Oracle Live SQL, the heading is somewhat meaningful. It will actually be the expression that was used to derive the value. But we can't always rely on that. Other tools might not be so friendly, or the process of deriving the value might be more complex than a simple function call. For that reason, we choose to apply a rename and give a more meaningful or descriptive heading to the column. In our next query, we examine the average function. The intention of this query is to return the average lab fee for all courses offered at the school. Notice there's no where clause, so the group of rows that we're dealing with here would be every row within the course table, all of the courses, regardless of sponsoring department. So average returns the average of the values in the specified column. Again, we're passing lab fee as the argument to the function. The value is computed as the sum of all the values in the column divided by the number of rows that contributed values. So we have 14 rows currently in our course table. Average applies only to numeric data or intervals. This is a date-time data type, a duration that has elapsed between 2 points in time. Recall that the data type of the argument column in the sum function determined the data type of the value returned by that function. The same is true of the average function. A quick look at the names of our next functions would suggest a simple, straightforward set of operations. But there's a little bit more to these. Min and max are functions that accept different types of data. They can accept numeric data, they can accept character data, and they can also accept date-time data. The min and max functions return for their result the same data type as the column to which they were applied. Again, similar behavior to the other aggregate functions we've examined. The names that I've chosen for my column headings suggest the difference that I wanted to bring to your attention. When we say lab fee is the argument to min and max, we're passing a numeric value. So thinking of min lab fee, well, that would be the minimum or the smallest lab fee. Max lab fee would suggest the largest or the maximum lab fee examined. So the column names here of smallest and largest seem to be in alignment with what we probably would interpret as the meanings of the min and the max functions. But when we apply min and max to character data or to date-time data, it doesn't quite seem to make sense if we say the smallest name and the largest name, or the smallest date or the largest date. But it makes more sense to me to say the first and the last. Remember, when we use the order by clause, or when we use a relational operator such as greater than or less than, we're talking about an ordering of the values. And effectively, that's what we're getting when we're dealing with min and max. The first one in the order and the last one within the order. So in this query, we demonstrate a couple things. We've introduced the new functions of min and max, but we're also showing you that we can have more than one aggregate function applied to the same column in a single query. And furthermore, we can apply aggregate functions to more than one column in the same query. Each of the aggregate functions we've discussed allows the use of the distinct keyword in conjunction with the column name that's passed to the function. Including distinct causes only unique values to be considered in the calculation of the function. That is, duplicates are removed from consideration. Using the keyword all causes the aggregate function to consider all of the values in the identified columns, including the duplicates. All is the default. The course table contains 2 rows for the CIS department that have a lab fee of $100. By applying the distinct keyword to the sum function, we'll be considering only one of those values. Although distinct can be used with any aggregate function, it serves no real purpose when applied to the max or the min function. The following query shows the difference between some lab fee and some distinct lab fee. The count function is generally defined as returning a number which reflects the count or the number of rows within a table. I think this general definition requires a little bit of clarification due to the different forms of arguments that can be passed to this function. There are actually 3 variations of the count function. Count asterisk simply counts the number of rows that have satisfied whatever selection condition is specified in the query. When you pass a column name as an argument to count, this counts the number of non-null values in the selected column. And the third form includes the distinct keyword. When you say distinct and put the name of a column, it counts the number of distinct non-null values that are present within the column. In general, there's no difference between the first 2 forms unless null values are present in the column that you specify. Again, count asterisk does not take the name of a specific column. It simply counts the number of rows which satisfy the selection criteria that you might specify in the where clause. If there is no where clause, it simply counts the total number of rows present within a table. The count asterisk form of the function is a little different than the other aggregate functions we've presented so far. Notice that the argument is asterisk rather than identifying a specific column name. The result of invoking this function in any of the forms is always going to be an integer. The result of the count function is not influenced by the data type of the argument passed to the function, as was the case with the other aggregate functions we examined. In our example here, we're applying the where clause to identify only those rows that are sponsored by the theology department. Given the current content of our database table, this will account for only 4 of the 14 rows that are present in the table. So count asterisk will return the value of 4. Again, because this is a derived value, we've chosen to rename the column with the heading of how many. If we had simply said select count asterisk from course and omitted the where clause, we would have received a value of 14, the number of rows in the entire course table. The use of the predicate in this example has a similar behavior to what we saw when we were talking about simple predicates and complex predicates, simply identifying the set of rows upon which the function will be applied. The distinct form of the count function can be used to determine the number of unique or distinct values that exist for the indicated column. The query that we present here answers the question, how many departments currently sponsor courses? Passed to the count function, in addition to the C department column, is the distinct keyword. The result of this query will indicate that there are 3 different departments which offer courses. If a department offers more than one course, it is counted only once due to the presence of the distinct keyword. Note also that C department was defined as not allowing null values. A null value present in the argument column would not be counted, but that's not relevant in this particular example. Our next example will examine that. But let's think a little bit more about this query. This is counting the number of departments that sponsors courses. Remember, we saw an earlier application of the distinct keyword outside the context of a function, which answered the question of which departments sponsor courses. In a future lecture entitled Missing Information, we'll discuss the null value in some detail. But for the moment, we'll just consider the impact of this null value on certain operations. So any null value present in the argument column will not be counted when we apply the count and use a column name, or distinct and use the column name. Here we're examining the staff table. We've not yet seen that in detail, so let me show you what that looks like. Observe the row for Da Vinci. The value in the department column is the null value. Different front-end tools display the presence of a null in different ways. Here, with Oracle Live SQL, it's simply shown as a hyphen. The presence of the null value in the department column of a row in the staff table means that that employee is currently not assigned to any department. Also note that the department column in the staff table does not serve as a foreign key the way that C department does in the course table. So the department column of the staff table has the following non-null values: engineering, math, philosophy, and theology. The one row that has a null value is the one that will be excluded from our count here. So count distinct does not count any null value, therefore we will see a count of 4. Note also that the values of philosophy and theology appear multiple times in this column. The use of the distinct keyword reports each value just one time, regardless of the number of rows in which the value is present. Well, that's as far as we'll go for the moment. We've introduced the basic aggregate functions: sum, average, min, max, and count. We explained how these functions operate and return a single value despite being passed multiple values. In our next video, we'll pick up to wrap up this lecture by introducing the concept of grouping. And this will involve introducing 2 new clauses, the group by clause and the having clause. Because the queries are starting to get more complex, including many more clauses than we originally saw, beyond simply select and from. We'll also introduce a concept that I came up with many years ago called the timeline to explain the points in time when particular aspects of the SQL statement will be evaluated. I think you'll find this useful and helpful in terms of understanding how to write a valid SQL statement and also how to understand a complex statement. I'm sure you're looking forward to that, and I'll see you next time.